All right, let's get started, everyone. Good morning, good afternoon, good evening, wherever you are. Welcome to our Cloud Lab. I'm Corey Summers, and I will be your host today. Joining me today are our wonderful CTO, Jorg Schad, and very specially, our software engineer, Anthony Mahana. So we've got a couple of housekeeping things to cover before we dive in. This will be a 60-minute session, folks. So what that means is we're going to do some setup, give you some great background on how all this works, and then we jump into the hands-on section. That's right. You're all going to get the opportunity to follow along hands-on, execute, and discover what's possible using some collaboration tools and notebooks and things like that. Submit your questions as we go. Okay, so in the question section, the chat section, put your questions in. We will address those mostly at the end. And we have a survey at the end as well. So please help us along to make these sessions better by filling out that survey. We'll also be sharing some other links and the slides to this presentation. As you can see here, we'll share all that out. All right, so without further ado, I'm going to hand over to Jorg, and we're going to jump in.
Yeah, as said, thanks for joining. What are we all about today? So I think large language models, GPT-4, etc., they're kind of like on everyone's mind right now, especially for the last 2 years. And what really gets me excited about LLMs is it's not necessarily just the hype that it's everywhere, but it's really that it is available to everyone, right? So I feel like even like my relatives, my uncle, etc., they're like, "Oh, I tried GPT-4," and those are people who otherwise wouldn't really understand what is going on with ML. So I think large language models and the easy accessibility have really made it being there and available for everyone. Then on the other hand, I mean, here we are at ArangoDB. So knowledge graphs is kind of the other side to that. And I think this is what we're going to like talk about. How can we combine both worlds and how can they enhance each other? I think one area where we definitely need to be careful is about hallucinations. And I mean, if you ever tried playing with GPT-4 or ChatGPT 3.5, any of those versions, you'll notice that sometimes you'll just get very weird answers. So, for example, if you research yourself, or we'll also see like more concrete stuff where it actually caused like business impact. For example, Air Canada or others, which like went in, put chatbots on their site, and then all of a sudden they figured out, oh, if my chatbot tells me you can rebook this flight, then this might actually be legally binding. And I think there was also another cars dealership. So hallucinations is basically when your large language models are just going to give you nonsense answers. And we'll talk about today how we can avoid that. And I think this also brings us to kind of like the challenge side. As said, like this webinar is about, we want to kind of close the gap in between large language models and knowledge graphs. So large language models, on the one hand, they are really strong at being a natural language interface. And I think this is what gets me so excited about them, because they really make a lot of ML, a lot of models available to everyone, because we are all used to like a natural language. And this means we get a lot more modes in which we can interact with IT, with databases, with all the other things out there. But there are also kind of like some of the downfalls of large language models, which we can also see here in the middle. And in my opinion, it mostly comes down to that we are leveraging large language models in two different ways. So if you send a query to ChatGPT, you actually do two things right now for a naive LLM question. And this is, first of all, you're leveraging the natural language capabilities. So the large language model is there. It will understand what you are querying it about. It will understand kind of what is your intent. And then on the other hand, we are using it to extract knowledge from the network itself. And I think this is where we really have a challenge, because large language models is basically built on top of neural networks, and neural networks, they are not great at storing data. And there are, for example, also studies showing that about 70% of the parameters, so 70% of the size of a large neural network, is actually contributed to storing like facts, And this is really what they are not good at. And we'll learn today about how we can separate that. On the other hand, we got knowledge graphs. Knowledge graphs are kind of the opposite, a very strongly structured representation. And I can represent like any domain-specific knowledge there. I can control who has access to that. But on the other hand, it's kind of hard to access. I need to learn a query language. I need to learn something like SQL, or in our case, AQL. And basically, often I will have a technical team in my company giving me access to that. And this is actually what we'll be talking today about. How can we combine both worlds? How can we give a natural language interface to your custom data? How can we leverage that, for example, for chatbots? How can we avoid hallucinations? And so basically, how can we get the best of both worlds? So how did we structure this? We'll start a little bit by motivating kind of the knowledge graph side. So what are actually the powers of graph, and why are graphs such a powerful representation? Also for building, training, or querying large language models. And then we'll jump into like more hands-on details. And I think then we'll try to spend like most of the time on really like hands-on exercise. And as Corey mentioned in the beginning, we will also share that so everyone can follow along and get hands-on experience with that. So just as a reminder, we actually live in a connected world. So if we are looking around us, for example, network asset management, in fraud security, it's usually we're not talking about like an individual data item, but we're talking about data in context. And I think this is what we typically will mean or refer to if we say like we live, or we're talking about connected data. We want to talk about not an individual item, but we want to talk about data in context. And in such a world, actually, graph is giving you the superpower to get deeper insights and get better results. Just one click, please. Exactly here. These are kind of like our graph superpowers. And maybe just to simplify that and showcase that with one example, entity resolution. This is like my personal struggle whenever I enter or fly anywhere. My name has this German umlaut in there. And so typically they're not going to spell that out, but it's going to be either spelled as just an O, as an OE. And therefore, whenever I check into a flight or anywhere else, I have to be like, is that really you? And I think this is really what entity resolution is about. And entity resolution is basically, we try to figure out that those two entities, they refer to like the same physical entity behind it. And this is a very common task all over the board, from cybersecurity, financial services, supply chain management, customer identification, marketing, where you want to figure out this is the same household. And of course, also, as said in my case, for just checking in into an airplane. Challenge here is we don't have like a single key which would identify me. I have different addresses because I have like an apartment in Germany. I've got an apartment over here in the US. I have different phone numbers, etc. So there's not like a single entity which can be used to identify this is actually me. So we actually have to do kind of like a context merge. We look at the context around, and if enough of the context matches, like phone numbers, they're almost the same, maybe like an area code is missing, something like that, country code, but otherwise it looks pretty much the same. And if we are fairly certain, we can actually merge those entities. But you already see, we can't just decide it from like one individual data item, but we need the data items in context. And I think this is what ArangoDB is a lot about. So ArangoDB at its core, it is a graph database. We support other data models as well. So basically you can also treat ArangoDB as you would do a document database, or as you would do like a Lucene Elasticsearch like search engine. And I think this is really where the power comes together, that we can combine all of that within one system. And you don't need to build up your system from multiple different data systems and then orchestrate them. Have a large open source community, and also we have graph machine learning and graph analytics on top of all of this, which we'll also dive to a bit later. But I think at its core, we are really this a very scalable graph database. So we are really good at handling data in this connected world. Okay, what makes us so special, or what also makes us so applicable? So first of all, in terms of scalability, we actually, if you look at the architecture, we have a division between so-called coordinators. So coordinators are kind of like the query endpoint you can connect to, and then they do exactly what their name says. They're coordinating a query. So basically, we have a transparent scaling, so we can add like nodes underneath, storage nodes, but we can also add like more specialized nodes. So for example, for machine learning training, for LLM training or LLM inference. And basically all of that comes together and we can pick like the right hardware for each of the tools. In some other solutions, I think people try to weave it into the storage nodes themselves. And there we experimented with that, but we figured out like, hey, it's really hard to find like the right hardware configuration. And then often you end up paying like a lot of money for expensive specialized hardware. I mean, those LLM trainings and also fast LLM inference can be quite demanding in terms of like specialized hardware. And you actually, a storage node for a database will have like way different requirements. So we actually, as part of our cluster, we kind of specialized nodes for specialized tasks. And I think that first of all allows us the scaling aspect mentioned earlier, but it also allows us to really have like dedicated nodes and dedicated performance for each of those jobs. That then brings us over to what we wanted to talk about. How can we actually combine that, or what is the challenge we are trying to solve with LLMs here? So right now, the status quo is kind of like we have a fleet of business analysts. They don't necessarily know for SQL, AQL, or any of those technical languages, but they need to interact with the storage graph. And so with that, it's basically right now the status quo is there might be an expert team. They really understand the underlying graphs. They understand the underlying technology. So if a business analyst comes with a new kind of like request or new area they have to investigate, those technical experts, they either build a new dashboard or they translate it into a query they can give to the business analyst. Challenges with that are obviously we have long turnaround times. It's a burden for the expert teams. They have enough other stuff to do, and it's really hard to get into a conversation where I not only have like a single question, but I have like an interaction, a chat. This is why it's like Chat GPT. It's called Chat GPT because we actually have like an ongoing interaction. And if that's always blocked by having like an expert needing to jump in, that will slow down the entire system. So with that, I would actually hand over to my colleague Anthony here, who will give us like a quick introduction to large language models.
Sure. Thank you, Jörg. So our detour on the powers of graph and ArangoDB is complete, so we can now talk about the other side, being LLMs. A quick reference, though, before we begin, if you're interested in a more academic approach to what we're about to speak today, we highly recommend this paper, which was originally published in June last year, but is still being maintained. I think it describes nicely the roadmap of how LLMs and KGs can interact with each other by splitting it out into 3 topics. And KGs enhanced LLMs being the first, where we essentially provide KGs as a knowledge source for training LLMs. Number 2 being LLM augmented KGs. So how can we leverage the natural language interface of an LLM to read and write KGs? And then as well, point number 3 being kind of a symbiotic relationship between both. For the purpose of this talk, we'll be focusing on point number 2 today, but we'll briefly cover as well point number 1. Okay. So nowadays, your interaction with LLMs is customizable to fit your specific needs, as it should be. So, you have the choice to use LLMs right out of the box for a quick deployment. If you need more tailored responses, prompt engineering is the way to go. It allows you to, shape the prompts to direct the model's output. There's also RAG, which stands for Retrieval-Augmented Generation. We'll talk about that in a second, but a quick overview, it's basically meant to integrate external knowledge bases to enrich your model's answers and, kind of improve that performance when LLMs kind of hallucinate. Fine-tuning is when you want the model to align more closely with your specific data or domain, which you can see in the code snippet on the right here. This is a quick sample of OpenAI's interface to fine-tuning a model. And so this helps adapt the model to understand the nuances of your use cases. lastly, if you're up for it and you've got the money and time, there's always the option to train a custom LLM, giving you full control over the training process and the data it learns from. So LLMs are trained on enormous bodies of data, but they aren't trained on your data. And so retrieval-augmented generation solves this problem by adding your data to the LLMs that they work with. And so RAG significantly improves the quality of answers by pulling in evidence from various data sources, which helps you prevent the model from generating inaccurate or unrelated information. It's about providing that interpretability since the answers are supported by retrievable data, essentially providing evidence for you to back up your query. For those with specialized needs, RAG can utilize custom data sets to produce answers that are more aligned with niche or industry-specific queries. So this basically keeps the data source up to date and ensures that the model responses remain relevant over time. And yeah, using RAG allows you to reuse the existing models, so you don't need to worry about training a new one. And so you're just optimizing the out-of-the-box solution provided. A cautionary tale, however, for RAG users, this is one of many articles that exemplifies what can happen when LLMs operate without the proper safeguards that RAG provides. So the case here illustrates a chatbot that's been integrated with a popular airline in Canada called Air Canada and without the checks and balances of RAG, it commits the organization to a promise it wasn't supposed to make. So the chatbot, possibly due to some kind of hallucination or misunderstanding in the training data, promised a discount that the airline was not able to, or the airline legally had to honor, and so this caused a big issue and set a big precedent from any organization that makes use of chatbots and is in the world of selling to customers. So what we're essentially trying to show here is the role of RAG in verifying information and ensuring that the LLM's outputs are accurate and align with the policies and commitments of the organization. So it's a practical example and it shows the potential costs. And so this is actually a good segue to graph RAG, which is a kind of a subset of RAG, and it's a leap forward in essentially addressing the limitations discussed earlier. So you're essentially querying against a knowledge graph, which provides more precise and contextually relevant answers. The user poses a natural language question which the LLM processes. And so instead of generating an answer based on solely on the learned patterns, the LLM can take advantage of a graph structure. So using vertices and edges interlinked in a database. You get a more accurate result here because it's based on the most current and connected data. And so this is one of the key steps into mitigating misinformation from LLMs. Going back to the principle of RAG, you're trying to offer answer evidence, and graph RAG achieves the same thing, but instead we just simply take advantage of a graph structure. Okay, so on the topic of knowledge graphs and also vector stores, when deciding on the data retrieval for LLMs, you have to consider both, as knowledge graphs offer the structured data with complex relationships when you need transparency and, let's say, domain-specific detail. Vector databases would be important if you want to handle unstructured data where speed and scalability is critical. And when working closely with machine learning models. In cases where you want to blend both, your choice should align with obviously your application's demands, but there are worlds where both can be utilized at the same time. Okay, and so our opinion on the evolution of LLM usage can be visualized here. So on the far left, you've got your naive LLM. And so this represents the basic model, which can generate content, but may incur costs, produce hallucinations, or invent information. And so we cannot utilize or verify the user-specific data. RAG with vector stores is when you use the LLM with retrieval-augmented generation to provide additional information retrieval. And so this reduces hallucination and pulls in external data. We have a nice slide coming up shortly to visualize that. But it's still not verifiable and lacks direct connection to the user's unique data. And so this is where we propose GraphRag coming in, being the most advanced solution in our opinion. And this allows us to take advantage of vertices and edges within the context of RAG to provide more user-specific information.
I mean, this actually comes into like a lot of questions I get. So I think for me, this is basically what we also had in the earlier slide, like, hey, when should I use a vector store? When should I use like a knowledge graph, etc.? And for me, kind of like this evolution is typical, like also how I see users starting, right? You send your first query to just your chat GPT, then you start adding RAG to kind of like import your own data into a vector store, because also the like first solutions, but then often you're still hitting some boundaries. So for example, we're working with a customer in the healthcare space, and for them, like a vector store is just not auditable, right? This is what we meant here by not verifiable. So I cannot actually check what's in there, because in the end, what do I have in a vector store? I have those embeddings. So I have like long sequences of number, which I like a domain expert cannot go in and verify that. I think the second aspect, and we saw that with another customer, was just an LLM. What we should be aware about, it's doing text embeddings, right? So it's really great at like this context scanning like a linear document. But on the other hand, and we've seen that, for example, in contracts, you often have something like, oh, this section is referencing this other section. So actually, like if you want to understand such kind of contract, you need to understand the context and you need to understand the graph structure. And again, this is something where they ran into limitations given basic RAG. And with GraphRag, because I'm preserving the context around that, they actually can benefit from using connected data. They can have a domain expert coming in and therefore also minimize the hallucinations in the end. All right, so with that, I think we covered like this one arc about like how can I get to like my custom LLM? How can I connect it to my custom data? And this was like the side here of RAG, GraphRag on the right. We have another dimension, and this is basically if your LLM doesn't perform well enough in terms of specific tasks. So, for example, we internally have fine-tuned a model, which we'll talk about on the next slides, for being better at translating, for example, SQL or natural language into AQL. So there, this is really nice about LLMs. They are so-called few-shot learners or even one-shot learner. If you give them just a few examples of what you actually expect, you can highly specialize them. Next slide, please. And yeah, this is basically what fine-tuning LLMs is about. So we take an existing base model, we give it just a few examples. Keep in mind, Anthony said like the initial training, it takes a really long time, but here we really need to give it just a few examples to get to pretty good results. So it's often just like somewhere between like 5 to 10 examples. And this actually gives us a fine-tuned LLM. And with that fine-tuned LLM, we can often also reduce the token cost. So for example, if you might have heard the term token, this is basically like a chunk of text, a token of text an LLM can process. And this is often also how you will be paying for ChatGPT or some of those other model services, like how much data how many tokens are you consuming? And fine-tuned LLMs can also really help you to get your token costs down and therefore also achieve like lower latency, because you'll basically bake it into the models. And as mentioned, this is, for example, what we did for natural language or Cypher to AQL translations, fine-tuning our model. The challenge is those large language models, they can be really big. So if you just look at like Llama 2, and there are even like larger ones available now, we're actually talking about 120 gigabytes. So question is, I said like you don't have to necessarily need a lot of data, and also the processing time is kind of okay for it, but just kind of like storing it and having the amounts of memory available for different models can grow rather rapidly. So imagine just you have like two fine-tuned models, 65 billion. Here 65 billion usually refers to the number of parameters. We have like 240 gigabytes, which ideally you have somewhere in memory for fast serving. What can we do about it? We can quantize this, and quantization basically refers to next slide, please. About choosing the amount of representation. So basically, this is why here it says like quantized for bits. If you're a bit familiar with IT, like we need certain data types to represent any of those parameters. During training, we want like a really high precision one. We want like all the kind of like dots after the comma or dot, right? We want really precise representation. But then later when serving, we can actually cut down that representation to, for example, here something like 4-bit. So we are identifying how can we best represent our parameters with a smaller data type. And this is what, for example, QLoRa is then also all about. How can we do efficient fine-tuning and quantize at the same time? Yeah, exactly. There's also like a comment on the chat, like 1-bit LLMs exactly coming up. Most things I'm seeing is somewhere around 4 bits still right now, but yeah, some people are even going more extreme. So when fine-tuning, what are my options, especially if I want to quantize? The naive way would be, I have my original matrix. This is like the blue square here. This is my 65 billion parameters out there. And I can either, so it was kind of like one of the first approaches, I can just store kind of like the delta, like how do I change each of those parameters? And because this is usually just like very small differences, and I still want to keep my original weights around anyhow, I only have to store the delta. So that already can cut down it by quite a bit, but then the QLoRa, and LoRa stands for low rank adaptation. So if you're familiar with algebra, matrix, and vector magic, you can actually take this weight matrix way up here on the right and kind of like decompose it into 2 vectors. So you're basically approximating it by just 2 vectors. And if our W has a dimension of, I don't know, 1,000 times 1,000, we can easily break that down into our vector A being 1,000 times 3 in terms of dimensions, and our vector B being like 1,000 times 4, for example. So these are kind of like ways by which we can really cut down the size we need to represent our fine-tuned models. And this is also why often we are able to have a larger number of fine-tuned models. We, for example, internally, we experimented there quite a bit with an Intel project called BigDL, which is doing both, which is doing like the low-rank adaptation side and then also the quantization side there.
Okay, so this is back to me now. We're going back to the synergies that LLMs use when playing with KGs. And so we see this in 2 ways. Firstly, we see them assisting in the generation of these knowledge graphs by parsing and understanding large data sets from data lakes or plain files into meaningful relationships and entities. This makes the creation process more efficient and insightful. So that's step 1, using LLMs to write KGs. Secondly, you can see LLMs being used to read KGs, i.e. retrieve and augment information from these graphs. They use the structured data within any graph database to provide the context-rich, accurate answers that a user or an analyst is expecting. And so this creates a powerful loop where the data is constantly being refined and expanded upon. And so going back to step 1, generation of KGs, you've got things like using LLMs to perform entity discovery. So this means to identify entities within the text. This can include people, places, organizations. You've got relationship extraction, so being able to create edges out of how the entities relate to each other or how they interact with each other, providing that into your KG. You've got co-reference resolution, so this means to understand, resolve the references in the text, such as pronouns or synonyms, to ensure that the entities are properly linked. Then you've got your end-to-end KG construction, so taking care of the entire process from raw text to a structured knowledge graph, schema design, model selection, all that stuff. And then text embeddings, or just embeddings in general, which allow you to generate vector representations of data to capture the semantic meaning, which can then be used again in your KG. So this is how you turn your data lakes and your plain text files into structured data using LLMs. We have an example of some of that later on, simplified in the Colab notebook. So then we can talk about how LLMs help you read KGs. We're essentially looking at two things here. One is how LLMs understand queries and how they facilitate a two-way conversation with the data. So firstly, you've got the powerful natural language interface from LLMs. And so the goal here would be to take a natural language query by an analyst and interpret it into the query language that you're looking for. So they don't just match the keywords with what you're asking. The goal here is to have the LLM understand the intent behind your questions. This means that users can ask complex questions as if they were talking to a human expert, not just a database. On the second point, you could, in theory, set up a feedback loop between the analyst and the LLM so that you can allow for iterative refinements over the query. So similar to interacting with ChatGPT, you've got your thumbs up, thumbs down buttons to give feedback. The same can apply here. You let the human guide the LLM to the result that you're looking for. And so all of this being said, it has the intention to basically lower the barrier of entry for interacting with KGs and query languages. You're trying to avoid the users from having to fully understand the ins and outs of a database schema or query syntax. They can just ask their question in plain English or any language and get the insights they need. And so the goal here is to democratize access to data-driven insights. Okay. We're just about to wrap up and get started to the actual lab. And so what I do need to give context to is because we'll be using two fundamental libraries, and one being LangChain and one being LlamaIndex. And so we're just going to give you a quick context to what these are. LangChain was introduced sometime last year, and it has been blowing up ever since. It's a framework that amplifies the usage of LLMs by integrating them with other systems and technologies. So you can think of it as the Swiss Army knife of LLMs right now, or the Swiss Army knife library of LLM usage. It's more than just about the language models. It's how you connect them to the rest of the tech stack, and how you take advantage of things like memory and building agents and using different LLM patterns and providing an interface for prompt engineering. And so this means that you can have LLMs conversing with databases, executing tasks through APIs, or interacting with users directly through some kind of app, all within one ecosystem. So we have a plugin for it, and so this is kind of our first step towards our LLM initiatives. The second library being or framework being LlamaIndex, and so this is more related to Retrieval-Augmented Generation because it takes the challenge of making LLMs understand and work with structured data head on. You're given the scaffolding needed to bring in data from diverse sources like database, files, APIs, and so you're making it accessible and usable through LLMs. This is critical. I mean, you're not expected to kind of work with LLMs out of the box nowadays if you want to make something useful out of it. And so think of it as giving your LLM a well-organized library of information it can pull from to make sure its responses are as accurate and informative as possible. Okay, this gives us to the lab. What I would suggest is you can follow along with me, and after that kind of experiment on your own. We've provided you with the output version of the notebook. And what that means is it already contains a set of outputs for each code cell that we have. So if you're just interested in not running the notebook, you just want to see the outputs, then I would recommend that one. So I've gone through the trouble of installing all the dependencies. I won't even bother about talking what we use here. I mean, you can find these on PyPy or Conda. It's your choice. But I do want to quickly mention we installed some OpenAI, LangChain, and LlamaIndex dependencies. We set our OpenAPI key or OpenAI API key. I chose GPT for this case. And so now we can talk about the setup. So what I can propose is we have 6 categories. And given the time constraint, probably won't do everything. But I do want to mention a bit about LangChain, just to kind of get things started. Going back to this idea of it being a Swiss Army knife, there are, I would say, 6 basic components in LangChain that you can make use of when building LLM applications. Just a quick intro. I mean, you can see here that the interface of your OpenAI LLM model can be provided through LangChain, and so they have a wide range of LLMs available through this LLMs module, OpenAI being one of them. Just a quick example of how that looks like. A simple instantiation of the OpenAI class via its constructor, setting the temperature to 0, implying less kind of spontaneous answers, more of a consistent feel, can give us the opportunity to ask it questions. And this is essentially here. This is where you're using the model out of the box. There's the equivalent of doing the same thing but providing some kind of prompt engineering to it. And so this is an example of where we provide the question as a string, and we kind of we pass it in via a parameter here via this keyword argument, but provide in the template a simple instruction to prompt engineer the model. You've got also the ability to make use of what's called chains, which are it's a data structure used to do a sequence of prompts back to back. And so this is an example here where we make use of what's called a conversation chain, where we can ask it a question and clarify our intention, our original intent via the second input using a different function call. And so in the previous example that I had shown, this would not have been possible via just the regular model.invoke method. It's just one context per invocation, whereas using this conversation chain can allow you to keep track of memory. So then here we can scroll down and talk about what it means to build an agent. So, you know, an agent in the world of LLMs is considered as a means to provide your LLM application with different tools or a subset of skills that they can make use of when a question pertains to that specific tool. And so in this case, we've instantiated a tools variable that is loaded with 2 things. One is the Wikipedia knowledge graph, or a similar sense to that, and 2 is a simple math tool used for just simple computations. And so here, once we initialize our agent, you're essentially asking it different questions, and you expect it to use the specific tool in mind. And so if you're familiar with this, I believe it's called action thought observation or thought action observation pattern, you can see something similar to that, where given a question, the observation is that it knows which tool to use to give the proper answer. And so the same thing here, you know, we ask it, what is ArangoDB? It observes that I guess here we've got something different, but you kind of get the idea of where I'm just reading the answer now. It looks like a part of the LangChain 01 update is that some of the tools have changed, but it's no problem. This is a quick example of what it looks like when an LLM hallucinates. So I ask it, what is ArangoDB? It assumes that it's supposed to use the LLM math module because it can't find the Wikipedia tool. But so we can go back now and move on. And so in this case, this is more of an example on using ChromaDB with LangChain to create a vector store and query it. I'll actually skip this part. The output is available on the other notebook. We've got 20 minutes left, so I'm going to try to move on. Okay, so quick intro to LangChain. Now the next intro is ArangoDB. I've instantiated a temporary ArangoDB instance using a Python package. And so what I quickly want to show you is what that data looks like. Looks like I got sorry, apologies. I took the username instead of the database name. There we go, password. And so I've loaded 2 data sets within this DB. One is the Game of Thrones data set. It's a graph related to Game of Thrones characters and their relationships via the child of Edge. And so here we can see, for example, that Arya Stark is the child of Ned Stark. Ned Stark also has a child called Brandstark, etc. It's a very small data set, like 12 vertices and 20 edges. The other equivalent data set, the other data set that we've introduced is from the GDELT source. It's a compilation of news reported by media sources across the world, and it ranges from peaceful protests to assassinations to battles to riots. And so it's a nice way to talk about kind of a real world example. Just a quick mention of that data set. However, I'm looking for the event collection. This is kind of the primary source of the data. Here's an example. So this is a very quick sample event here where we talk about the news source and some data around it. Okay, so we have the data, it's in our DB. Now let's move on to configuring LangChain. And so the first thing you do when configuring LangChain with ArangoDB is you import the Arango graph class from the graphs module. This is responsible for creating a schema out of your ArangoDB graph. And so what you're given here is essentially your graph representation of each graph. So you're given two graphs in this case. You've got your Game of Thrones graph right here with the what we refer to as edge definitions in ArangoDB, or similar to edge types if you're familiar with PyTorch or any other edge graph library. Then you've got your open intelligence data set, which is a bit more complicated. And you also are given a collection schema. So as you're querying the database using the LLMs, your LLM is given this information to get a better understanding of what your data or what should be expected from the data. Okay, so moving on. Next thing we do, similar to that OpenAI class that we instantiated, we can instantiate the chat OpenAI class. Ignore this deprecation warning. This is just a matter of bumping LangChain to a different version. But now we can see that if I quickly just show you the model that we instantiate, you're essentially given just the typical model ready to be used. And so then the final part is to create that Arango graph question answering chain, which provides the graph data structure that we previously created and the model that we've just created. Okay, so we're given this chain output. And so from here, we can start prompting. This prompting section is divided into two, one for each data set. We'll do a few examples here for both data sets, then we'll move on to the other sections. Very simple example, who are the two youngest characters in the database? We can see here that without even knowing which character collection to use, or without even specifying the character collection, just by asking this question with two different data sets in the database, the LLM is able to reason that, okay, you must be talking about the characters collection from Game of Thrones. We can do a simple AQL query here to give you that answer. And so you're basically, you've got in return a data structure. It's a dictionary, but if you're only interested, of course, in the string response, you can just fetch that via the key. Okay.
So Anthony,
yeah,
just to clarify, that was translated automatically into AQL, which is really one of the key elements of this, accessing all the power of Arango, correct?
Yeah, correct. So, you could start seeing a world where AQL becomes a middle layer between the answer, what you're asking and the answer you're looking for. One less language to worry about. And so moving on, another simple one is, let's try this one. How are Bran Stark and Arya Stark related? You can see here that it does any traversal from Bran Stark and filters for a key that matches Arya Stark. It's referring to Arya Stark here as one word because we've provided a schema with an example document, and it's able to deduce that, okay, based on the example document, I'm going to assume that the keys look like this. And so we're able to give the answer by saying, yeah, Bran Stark and Arya Stark are related as their siblings.
And because we loaded the graph structure, that's how AQL knows how to translate that prompt into the AQL. Is that right?
That's right. Yeah. And so that schema is a core component to being able to leverage this query capability.
That's very elegant. Thank you.
You've got also other things. I mean, we can skip some stuff, like, we said natural language for English, but I mean, it also applies to any other language. This is a German equivalent of asking how old is Rickard Stark. I'll skip some stuff. You guys can check out the outputs later, but I do want to mention you can create, ask the LLM model to create data instead of just reading. And so here we have a query to add Jon Snow as a character. And so then we can add create a child of from Jon Snow to Ned Stark, and you can see that query here and its response right here.
And Jorg, how does this translate into something like fraud or cyber for an analyst to use this natural language interface instead of all that coding?
Yeah, it basically enables you to have this, what we mentioned in the beginning, the fast iteration, right? I think there was a very good question earlier. And maybe that's good to distinguish, like, for example, you can use to a certain degree, you can use it to detect anomalies. What I would see, this is actually where LLMs are kind of the front end, but in the end, especially if you look at ArangoDB earlier, we mentioned there's like Graph Analytics, GraphML. Graph Analytics and GraphML, they're very powerful at detecting, for example, anomalies. But LLMs, this gives me the interface to do like really quickly iterations on querying different scenarios, and therefore getting better outcome in there.
Right. And so what I recommend we do now is we can quickly go to the Open Intelligence demo. I'll stop with the Game of Thrones and quickly talk about another set of data sets. So here we could say, I quickly showed you a sample event. Let's say fetch me 3 events that happened in December 2019. From here, it's able to use the filter clause to get the date, and you're given a set of events that can be reviewed by the LLM model. You can have it answer traverse specific nodes. So if you're looking for a specific event, then you can get the name. This is a quick thing we didn't get to show in the Game of Thrones data set, but we have the ability to self-correct if the AQL query does not originally execute properly, right? So going back to this idea of a feedback loop is, the LLMs may hallucinate, they may not be able to get the query on the first try, and so this is a classic example of here saying, okay, well, you've done the query correctly, but you're just missing the event collection in the with clause in AQL. And so we pass that error message back to the LLM, and it comes back with a corrected version. Yeah.
So Anthony, I could ask a question like, show me the anomalous transactions over $10 million in the last 2 days, and then show me all the bank accounts associated with that and the bank account owners, since we have that document support, right? That's the power of this, correct?
Correct. Yeah. So we've done this for these sample data sets, but in theory, you can apply this to your use case, whether it be financial, security, chemistry, whatever.
Yeah. Anthony, there's actually a really good question right now. So what happens if there's like a typo in the generated query? And I think this is some of the magic, and you briefly touched upon LangChain. So LangChain is not just like a one-time translation. So actually, like if a query, like imagine the LLM is generating an invalid query, we would actually get back an error message, so we can validate that with the database. If we get an error message, like in the background, we would actually automatically retry and kind of feed that error message back to the LLM and generate a better query. And obviously, we'll only do that many times. But I think that's still important to realize. Like this translation, it's not like a one-off. You don't just feed it and you get an AQL back. There's kind of like a more kind of like logic behind it, especially like retries and kind of iteratively improving up on the query.
Cool. Moving on. I mean, we didn't mention this, but ArangoDB is multi-model by default. And what that means is we provide a document database, key value pair database, graph database, and search engine all into one. And so we can actually see here a component of leveraging LLMs within the context of our search engine. This requires a bit more of a Python setup. We refer to as creating a ArangoDB view and an ArangoDB analyzer. I won't go into this demo right now because we need a bit more time than we have, but just know that these LLM tools can leverage any model aspect of ArangoDB. It's not just graph, right? You don't need to have your data as a graph in ArangoDB to take advantage of this. You can do searching. You can just consider just a key value pair using LLMs to fetch certain keys.
This is critical, folks, because the fact that you can have all that data within a single platform, I mean, you'd have to write LLM interfaces to each disparate database if you had a graph only system, a document, a search, and then somehow paste them together. It's just not viable. This is all in one. So thanks for pointing that out.
Yeah. So, I mean, yeah, I won't run these now, but you could simply go down to the output section of the prompting for Open Intelligence, and you'll get, sample results in green for all of these queries. Okay. So I do want to talk about prompt engineering because we did mention this in our slides. So you have certain queries that tend to result in hallucination from the LLM side. So going back to our Game of Thrones data set, a simple example would be asking the LLM who are the grandchildren of Rickard Stark. And so notice how this query is syntactically correct, but it's returning an empty result. And this is often a mistake an LLM will make, especially with AQL regarding our use of outbound and inbound. If you're familiar with AQL, this is a way of specifying the traversal direction. And so a simple way to fix this would be to add in your prompt to remember to use the inbound direction. But that can get quite annoying as you're constantly correcting the LLM per prompt. We can see here that we can establish that these are the following grandchildren of Rickard Stark. So what we can suggest is provide a class variable to your chain object so that we can specify examples to promote few-shot learning for the LLM. And this is done by specifying a multi-line string in Python with a question at the beginning, such as who are the children of Rickard Stark, providing the correct version of the query, and then doing, whatever other examples you'd like to provide. And so rerunning this should be able to apply the pattern that we've defined to any other character now, right? So the LLM can deduce that, okay, you've just asked who are the grandchildren of Tywin Lannister. It's not the same as Rickard Stark, but I can see that you've provided a pattern for this kind of question using the proper traversal method to use. And so I'm going to use that pattern to answer properly this time. Right, so this is a nice way of leveraging prompt engineering as quick as possible. You've got other prompt modifiers we won't cover right now for the chain object. I'll leave that for you to take a look at. The alternative to prompt engineering via this AQL examples object is to rely on the prompt template class of LangChain. Once again, I won't do this now, but essentially the chain object that we've built has the prompt templates exposed for each section. That means from natural language to AQL, this is the instruction we provide to the LLM. From AQL error to AQL result, this is the prompt template we provide. And then from AQL result to natural language, this is the prompt template to provide, right? So these are exposed and these can be modified to then create your own version of this ArangoDB chain that you're building. So we're not taking credit for the prompt engineering behind it. It's up to you to decide if you want to use the predefined templates. In this particular example, we modify the last one to basically add this last line here. And so if we quickly do it, I'm going to see if I can just run this real quick so that you can take a look at the difference. So we've instantiated our sarcastic chain. And then if we ask, is Ned Stark alive? It'll still do the query, but the difference now is that it gives us a more sarcastic and humorous answer. All through this, just one line here changed. Okay. Your other option, if you don't want prompt engineering, that's fine. Fine tuning is also possible. In this case, we've provided some small code cells here to give you an example of what it looks like to fine tune a GPT model based on AQL data. And so we've defined some training data here. It's the same thing over and over. We've repeated it 10 times, but just to give you an idea, you've basically provided a message clause with the content of the question, which is asked by the user, and then the content of the answer, which is provided by the assistant. And so this allows you to create a fine-tuning job to fine-tune the GPT-3.5 model to give you a different chain now. And so, yeah, super useful tool. I will conclude on this LlamaIndex demo. We talked about what LlamaIndex is. It's a framework for RAG. It's got a lot of different tools at your disposal. I do want to mention that what we're about to do is an alternative to query answering via AQL. What we're about to do is we're about to perform query answering or question answering, I'm sorry, without the use of AQL. You'll be using embeddings to create semantic similarity between the query that the question I'm asking and the embedding version of the documents. So LlamaIndex has a class called Simple ArangoDB Reader, and it loads the data into a list called event documents. And then so what we'll do is we'll create a vector store index out of the first 3,000 events and give you a event query engine at your disposal. This will take a few seconds. So while I load this, I'm just going to switch over to the output version just so that we can save on time while it loads. I'm going to scroll all the way down and go back to where we are. And so after this loads, you have at your disposal a query engine that you can use to ask it questions. So in this case, if I use the query engine here to say, tell me about a protest, it's not using AQL to fetch this data. It's creating an embedding version or a vector representation of your query and using a similarity algorithm to compare it against the embedding version of the events that have been provided in the vector store. And so this is going back to what RAG is. RAG is about providing answer evidence. And this is it. You're looking at the evidence. You're asking it a question and you're given back even the exact ID from where it got this event from or this data from. And so continuing off of the output example, because I probably won't have time to load everything, you can even create one for the actor collection. This is another collection that's tied to the events via an edge. This is simply representing the names of certain actors responsible for said events. Same thing. Here you have an actor index that you're at your disposal. You can combine them via creating a query engine tool. This is going back to that agent concept. So this time you're basically creating a multi-RAG application that allows you to use the specific tool whenever needed. So going back to that Wikipedia versus LLM math example, this is the same thing. We've created two tools, one for event collections and one for actors. We can ask it different questions and it will know which tool to use based on the intent of your question. Okay, all of this is at your disposal. I'm going to go back to the slides now. Okay, so Jörg, I think at this point, I'll hand this off to you.
Yeah. So I think there were some really interesting questions, just kind of like as outlook. So as mentioned, we are also doing a lot of work with graph machine learning. And if you look at graph machine learning, in the end, it is about how can we create the best embeddings, the best vectors for your graph and then basically solve tests there. And if you're a bit familiar what's happening underneath LLMs, I mean, we mentioned vector stores, for example. What an LLM basically does, it takes natural language and it turns it also into an embedding, or the other term being used there, if you come from the vector store perspective, is a vector. In the end, this is just like a long sequence of numbers, but this actually works pretty much the same. And next slide. This is also, for example, something we're very excited about, that we can combine that. I think there was a question about this multi-model aspect. In that embedding space, in this vector space, we can actually take different embeddings coming from natural language, coming from graphs, and then actually interact with them. So find like a similarity in between, as long as we choose like our embedding functions, right? And unfortunately, we don't have enough time, but I think this is a very, very interesting area how we as a team, we are also working on combining that power of LLMs and combining the power of like connected data and graph machine learning here. So if we would just look at that, like the next evolution of like LLM usage, even taking it like beyond GraphRag, is like not just taking an LLM, which is not optimized for creating embeddings for a graph, but actually leverage our ArangoML embedding capabilities and even generate like really the best graph embeddings out there. So that would give you kind of like another boost in terms of just performance and in terms of like the quality of the embeddings you have. So that just is kind of like a small outlook. I know we're out of time. By the way, great questions. I can't quite follow in answering all of them as quickly, but we'll still be around trying to answer more.
Yeah, and just one other thing, if you'd like to discuss your specific use case based on this, finance, cyber, whatever it is, and dive a level deeper on how you can do that, simply go to our website and schedule a call. Our technical team will schedule a call and we'll dive into that specific thing based on everything that Jörg and Anthony have just shared. Awesome job, guys. Also in the chat, we have all the resources here, the slide deck, the notebook, everything else. We also have a survey we would love you to fill out. We will be sharing the recording. And with that, we're going to say, again, thank you all for joining. Great session. Thank you, Jörg and Anthony. Until next time.